Hi, welcome to another practical session in which we are learning spatial statistics and spatial econometrics using the R programming language. My name is Saif Ali. Today's topic is fitting model variograms, and this continues from previous topics and previous understanding. We are focusing in these sessions on developing programming skills using R that are needed to conduct spatial statistics and spatial econometric operations. But the acquisition of these programming skills relies critically on conceptual understanding, which you will obtain by watching and learning from the theoretical lectures. So for each practical session, we go through the conceptual understanding and the theories and principles that you need to already know in order to maximize your benefit and maximize your skill acquisition from these settings. Today, in these sessions, what would be great is if you, for your conceptual understanding, what we should already know is the idea of variograms, both omnidirectional and directional variograms, which is something that we've done in previous sessions. You should know what they are. You should also know how to estimate them using R, because this is all material that's already been covered. It would be good to have a notion, some understanding of model fitting. How do you fit a function to some data? What does it mean to fit a function to data? It would be nice if you at least conceptually know what this is, what is the meaning of fitting a function to data, because this is something that we will do today, but I will not be able to go into the theoretical background. So if you're familiar with model fitting, good. If you're not, I recommend that you pause this video and review some material online or from some textbooks, or maybe ask your teachers and friends. This is something that you will need to understand in order to appreciate the material fully today. You should already know from this course variogram models, the spherical variogram, the spherical model variogram, exponential, and others, what they look like and how they differ from each other, and what are the parameters of a variogram, of a fitted variogram. These terms, the sill, the nugget, and the range, these were covered in this course in the theoretical sessions. So please go and review them if they sound unfamiliar, and if they're familiar to you, then that's great. So in terms of programming skills, what should we already have done? Well, we should already know how to estimate variograms using the Muse dataset, both directional and omnidirectional variograms. This is something that ideally you should have gone back and done many times on your own, played with the various function arguments and parameters. So it's something that you really, it's kind of, from the back of your hand. So we can build upon it. And so today what we'll do is we'll change things up a little bit, and we will use a different data set. We will not rely on the Muse data set for heavy metal concentrations that we've been using. We will actually import some data that we get. This is real world data that we got from a public government data portal. And then we will fit a model variogram. So we will we will load a new data set, we will estimate a variogram, and then fit a model variogram to it. That's what we will do today. Just a quick review. What is an experimental variogram? Well, it's a function of spatial lag, as you see on this figure. On the x-axis, we have spatial lag denoted by h, and this gives us a value of variation or variance for some set of spatial lags, for some discrete points on the x-axis. So for h values, 1, 2, 3, maybe 10 to 20 values of spatial lag, we know the value of semivariance. So we have some idea that at these different values of h, this is the value of variance in zinc concentrations, for example. But that's not what we want. We actually want, for what we want to do in the future, we want a value for any value of h. We want to know the variance at any value of spatial lag. So even, for example, from this experimental variogram, we don't know how the variance varies between this point and this point. All the points that are in between, all the values of h, we don't know the behavior of the function. So, but that's important for us for what we want to do in the future. So what we can do is, one idea is that we use in geostatistics is we try to fit some smooth function through these points. And the idea is that this smooth function is continuous, so we can get a value of variance or semi-variance for any value of h without sacrificing a lot of accuracy, because our belief is that this function fits these points pretty well. And we should also be able to say or quantify how good the fit is. If it's not a very good fit, then we have to question our choice of function and try a different one. And we should also be able to compare one fit from the other. So if we fit two different functions, we should know which one we prefer based on some quantified measure. That's the basic idea of fitting a model variogram. This red curve that I've drawn, I've just drawn this by hand, but we actually want to use a closed form function, and this is called a model variogram. So the initially estimated points, those set of points, is called the experimental or the estimated variogram, and the fitted variogram is called the fitted model variogram, or just simply the model variogram. So this is what we want to achieve today using R on a brand new data set. So if this is clear, that's great. We'll move forward. If anything is not clear, please go back and review the video or previous materials if you need to. You can pause the video now and go back, and I'll be right here when you come back. Meanwhile, I'll move on to our live coding session with R. So let's go to the code. We have some new stuff today. I will go through it one by one. So this stuff you know. Let's load our libraries, GStat and SP. So the first thing we want to do is we want to load a new data set. We're not working anymore with the Muse data set. We will work with groundwater level data. So you know the groundwater level is the depth at which the water table exists beneath the surface of the ground. So if the surface of the ground is at level 0 and the water table where you start getting water from the underground aquifer is at, let's say, 3 or 4 meters, then that exact measure of where the water table is from the ground surface is called the groundwater level. So in that case, it would be 3 or 4 meters. And the government of India and various states in India, we monitor groundwater levels all over the countries using observation wells. And this data is available publicly on the India Water Resource Information System, WRIS. So I encourage you to check out this portal. I've already downloaded and formatted and sort of cleaned this data for you. We'll make it available for you. So it is, I have it here in my computer inside a folder called data as a CSV file. So remember, CSV means comma separated value files, and this is basically just tabular data. So the way to read CSV files is using a function called read.csv, and we store it in this R object called up.gwl, which stands for Uttar Pradesh groundwater level. So let's read in this file, and now we want to know what's in this file. We don't know what we've loaded, so we first want to look at it. So let's open it up by clicking the object here. And look at the column names. So we have district. That's simple enough. This is the district in which the groundwater level observation is being made. Then the block, which is a sub-district administrative unit. And then the hydrograph station, which is the name of the station where the groundwater is being monitored. This is the longitude and latitude, the spatial coordinates of that station, of the groundwater monitoring station. As you can see, we have spatial coordinates for some of the stations, but not all. Some of them are missing. and we'll have to remove these missing values, because if you don't know the spatial location of an observation, then you can't really use it in spatial statistics. So it is important that we know the spatial location. If the latitude and longitude missing, there's not much we can do. So we have to remove those observations. Type of station, don't worry about that too much. Year, this is the year in which the observation was made, and then pre-monsoon and post-monsoon. So in UP, they make 2 observations, one in pre-monsoon, which is around May, just before the rains start, and one in post-monsoon in September when it ends, or when most of the monsoon ends. The idea is that they want to get a sense of how much the rain recharged the aquifer. So they measure the level before the rain and then after the rain, and then they compare how much the level rose because of the rain. So that gives you a sense of how much water you have to spend for the rest of the year. So this is what the data looks like. Of course, we could have also just done head, UP, remember head, the command head, right? So if you just type head, it would have shown you the same information, but I prefer to just preview the data by clicking on the name of the object here. So now that we know what's inside, what we can do is, so we're not going to estimate the variogram for all of the data. So as you can see, there's a column called year. And so this data is for many years of monitoring. So for every year at every well, they made 2 observations, and then this is sort of the data that's been collated. So, so we can use the function called range to check how many years we have in the data. And the range is from 2009 to 2018. That's the minimum and maximum value for year. So let's say we want to estimate the variogram for a particular year, somewhere in the middle of that period. So I've chosen the year 2015. And this is a new command that you don't know yet. So this is called subset. So what this does is, from this data object, it picks only the observations where the year column equals 2015. So this will just pick out the rows for the year 2015 and store it in a new object, which I've indicated by .2015. So UP groundwater level for 2015. So if we run this, we will get a new object. So we will select data only for the year 2015. So if you see how many rows there were in the first, there was about 88,490 rows. But if you look at how many rows there are for the year 2015, it's only 193. So we only have 193 points. Sorry, that's not what I meant to do. It's not Western UP yet. It's UP, yeah. So we have 8,849. So it's considerably less, obviously, because this is data. This is the data just for 1 year. Now we want to go further. So remember this. This is something new, subset. This is something we haven't encountered. So we can use subset again. I don't want to, for this exercise, I don't want to estimate the variogram for the whole state of Uttar Pradesh. I just want to do it for some districts in Western UP. And the reason for this is, of course, efficiency, because some of the routines to estimate these things, they take a while. If you do it for the whole state, we'll be here for a long time. And also, sometimes doing things for the whole state is, stationarity is a problem, because you can't really argue that there is one process that governs groundwater level dynamics in the whole state. But for Western UP, you can make a stronger argument. You can say it's kind of under one river basin, one aquifer. Conditions are more uniform. It's a smaller area. So stationarity is a more reasonable sort of assumption. So again, I subset my data for 2015. And my condition for subsetting is that this district column, so this is a new operator called in. So this is the word in sandwiched between 2 percentage signs. What this means is that district should be one of these. It should be in one of these values. So I only want data for Muzaffarnagar, Ghaziabad, Baghpat, Meerut, and Hapur. So let's go ahead and run that. So now we want to see how many observations we have in this. We had 8,000 or so observations for 2015, but if you reduce the spatial extent just to these districts, we're left with 245 points. So that's kind of what we're working with, is about 245 observations. Now, remember, we have to convert this into a spatial data frame. We can't just use it directly. So let's convert it to a spatial data frame. Now, I get an error here. So it says missing values in object, right? So I told you that you cannot convert something to a spatial data frame if it has missing coordinates. It doesn't know what to do where the coordinates are missing. So we have to run this line of code, which is called na.omit. This is a function that basically removes all observations where there are missing values. So if in this data, if there are missing values in any of these columns, it will remove the whole observation. This is something called list-wise deletion. So we have to do this. Now, obviously, we're losing data this way. So this is not something you should do very sort of without thinking about it. This is something you should document. But for now, we're going to remove these because we simply cannot do anything for observations where we don't know the spatial coordinates. So let's get rid of the missing data and then run the coordinates. So now this time it did not complain. Now we have a spatial, let's make sure we have a spatial points data frame. Yes, so the class of the type of our object. So our data is now contained in this object called Western UP GWL.2015. So these are the groundwater levels for Western UP for the year 2015. Now, before we go forward, we want to do one more thing. We want a map of UP because now we're going to plot, we also want to see our values on an actual map. And maps are available in something called shapefiles. And in order to work with shapefiles, you need this library called RGDAL. So you'll have to install this. I've already installed it. So let's go ahead and load it and then read a shapefile for India, which is read by a function called read OGR. And I put the shapefile in the data folder, and we'll share this with you. So let's read this shapefile, and then again we don't want the whole of India. So if you plot this shapefile, we'll get a plot of all of India, but that's not what we want. We only want the districts that we care about, 4 districts. So we select those districts from the shapefile, and now if we plot it again, we only have those districts. So that's our kind of study area. We want to study groundwater levels in these 4 districts for the year 2015. So before we estimate anything, let's just plot our data in a nice plot. And I'm not going to go through this code in the interest of time. I encourage you to read this code on your own. This is not really code that is doing anything related to spatial statistics. It's just code to plot a set of points and a map together on one graph. This is done with a library called tmap. And if you go through this code, you will figure out what's happening. I'm just going to run it, and I'm going to show you what the map looks like. So it returns an object called westup.map. And then if we plot that, we see our data plotted on a map. So let me zoom this in for you. Oops, our legend entry is wrong. It says percent missingness. So we don't want that. We want to name it what it actually is, which is groundwater level. And these are post-monsoon groundwater levels, okay? I have selected the post-monsoon column. Remember, we had a pre-monsoon and a post-monsoon, so I'm going to estimate a variogram for the post-monsoon observations. So groundwater level post-monsoon, Western UP 2015. It's actually just a part of Western UP, but that's good enough for now as a title. So let's run this again, and let's see the map again. And now we have the right title, groundwater level post-monsoon Western UP. Let's zoom this in and see. So remember, the first thing that we did last time was try to spot if there is a kind of trend. Is there some obvious trend? If there's an obvious trend, then stationarity is not a valid assumption. I'm going to say I can't really see a trend in this data, but it does seem like in this area the circles are a bit bigger, whereas here they're a bit smaller, then here again maybe a little bit bigger. But I don't see an obvious sort of direction in which the circles get progressively bigger to smaller or smaller to bigger. Some other people may argue otherwise. That's why a lot of these things involve an artistic kind of modeling decision. But for now, I'm going to go with a stationarity assumption and assume a constant mean. So remember that when we assume a constant mean, we estimate our variogram using the formula where the right-hand side is 1. Basically, we're saying that the mean is constant. We are regressing on a constant. We're not estimating the trend using some covariates. So let's estimate our variogram and then plot it, and we get something that looks like this. This is our experimental variogram. So what we've done is we've replicated the same process from last time that we did on the Muse data set. This time, we've done it on a new data set. So we haven't done anything new. We've just got some new data. You should know what this is, hopefully, from your previous knowledge. Now we want to go further. We want to actually come to what we want to do today, which is that we want to fit a model variogram to this experimental variogram. And the way we do that is by using a function called fit.variogram. And this function, as the first parameter, takes the estimated variogram. What are we fitting to? And as a second function, it takes something called a model, which is given by creating an object of type VGM. And if you just hover over this, the first parameter of VGM is something called a partial CIL. Second is the model. Third is the range. Fourth is nugget, and then a bunch of other parameters. So if you look at this kind of variogram, so that's weird because a partial CIL, nugget, these are things that we find out after we have a fit. So why is it asking us to provide them before we fitted anything? Well, this is where we don't put the exact values, we put our best guesses. So remember a partial CIL from your conceptual theoretical lectures, a CIL is the maximum value of variance. So here the maximum value of variance is something like 50 or somewhere between 40 and 50. So as a best guess, I've put 40, right? This is the model. So what function do you want to fit to your variogram? So here I'm fitting a spherical function. So the code for that is SPH. I'm also doing another fit where I'm using the exponential model. So I'm going to try and compare these two fits. 0.4 is the range. So the range is the lag, the distance at which it reaches the maximum value. So I'm going to say the variogram kind of reaches a maximum value somewhere around here. So best guess 0.4. And then the nugget. So the nugget is, remember, the variance at h equals 0. So if I just extrapolate, so maybe the nugget is somewhere here. So as a best guess, I've given 5. So what's expected is that we look at the estimated variogram and we make our best estimates and pass them here. And then it will use an iterative algorithm, a weighted least squares method to try and fit the best, to arrive at the best fit. You can use different methods for fitting. You can use unweighted least squares. You can use restricted maximum likelihood. And if you want to explore different methods, I encourage you to read the manual. The way to do it is using a parameter called fit.method, in which you can provide which method you want it to use when fitting the function. By default, it uses weighted least squares, WLS. So I'm just going to leave it at that. I won't go into that. I'm going to fit a spherical function and an exponential function. And then I will plot both the experimental variogram as well as the fitted spherical variogram on one plot. And we get something like this. So just visually looking at it, seems to be a reasonably good fit. The line seems to fit the points well. But we would like a quantitative measure for goodness of fit. So one measure that sometimes people use is sum of squared errors for the weighted least squares that was used to fit the function to the points. And for the spherical, the weighted least squares is something like 159.0739, and then the sum of squared errors for the exponential one is 363. So it seems the spherical function is a slightly better, or rather a better fit. So so that's just a measure that you have to know, which one is a better fit to justify in your reports and your papers. So it seems for us, in our case, the spherical function is a better fit. So I'm going to stick with that for going forward. All right, I'm going to stop there and summarize what we did today. We estimated a variogram using a new data set for groundwater levels. We kind of left behind the Muse data set. We learned how to load and plot a shapefile, which is a useful thing to do for spatial stats. And then we fitted a variogram model, a spherical variogram model, to our estimated variogram. We came across two new libraries, TMAP and RGDAL. And I hope you find this session useful. Please review it. Please play with the code on your own. Try to change the parameters. Try using different models to fit your function. And once you're comfortable, we'll see you in the next session. Thank you very much.